In this video, I'm going to give an overview of various types of models that have been used for sequences. I'll start with the simplest kinds of models, which are auto-regressive models, that just try and predict the next term in a sequence from some previous terms. I'll talk about more elaborate variants of them using hidden units. And then I'll talk about more interesting kinds of models that have hidden state and hidden dynamics. These include linear dynamical systems and hidden Markov models. Both of these are quite complicated kinds of models, and I don't expect you to understand all the details of them. The main point of mentioning them is to be able to show how recurrent neural networks are related to models of that kind. When we're using machine learning to model sequences, we often want to turn one sequence into another sequence. For example, we might want to turn English words into French words, or we might want to take a sequence of sound pressures and turn it into a sequence of word identities, which is what's happening in speech recognition. Sometimes we don't have a separate target sequence, and in that case we can get a teaching signal by trying to predict the next term in the input sequence. So the target output sequence is simply the input sequence with an advance of one time step. This seems much more natural than trying to predict one pixel in an image from all the other pixels, or one patch of an image from the rest of the image. One reason it probably seems more natural is that for temporal sequences there's a natural order to do the predictions in, whereas for images it's not clear what you should predict from what. But in fact, a similar approach works very well for images. When we predict the next term in a sequence, it blurs the distinction between supervised and unsupervised learning that I made at the beginning of the course. So we use methods that were designed for supervised learning to predict the next term, but we don't require a separate teaching signal. So in that sense it's unsupervised. I'm now going to give a quick review of some of the other models of sequences before we get on to using recurrent neural nets to model sequences. So a nice simple model for sequences that doesn't have any memory is an auto-regressive model. What that does is take some previous terms in the sequence and try and predict the next term basically as a weighted average of previous terms. The previous terms might be individual values, or they might be whole vectors, and a linear autoregressive model would just take a weighted average of those to predict the next term. We can make that considerably more complicated by adding hidden units. So in a feed-forward neural net, we might take some previous input terms, put them through some hidden units, and predict the next term. Memoryless models are only one subclass of models that can be used for sequences. We can think about ways of generating sequences, and one very natural way to generate a sequence is to have a model that has some hidden state, which has its own internal dynamics. So the hidden state evolves according to its internal dynamics, and the hidden state also produces observations, and we get to see those observations. That's a much more interesting kind of model. It can store information in its hidden state for a long time. Unlike the memoryless models, there's no simple bound to how far we have to look back before we can be sure it's not affecting things. If the dynamics of the hidden state is noisy, and the way it generates outputs from its hidden state is noisy, then by observing the output of a generative model like this, you can never know for sure what its hidden state was. The best you can do is to infer a probability distribution over the space of all possible hidden state vectors. You can know that it's probably in some part of the space and not another part of the space, but you can't pin it down exactly. So with a generative model like this, if you get to observe what it produces, and you now try to infer what the hidden state was, in general that's very hard, but there's two types of hidden state model for which the computation is tractable. That is, there's a fairly straightforward computation that allows you to infer the probability distribution over the hidden state vectors that might have caused the data. Of course, when we do this and apply it to real data, we're assuming that the real data is generated by our model. So that's typically what we do when we're modelling things. We assume the data was generated by the model, and then we infer what state the model must have been in order to generate that data. The next 3 slides are mainly intended for people who already know about the 2 types of hidden state model I'm going to describe. The point of the slides is so that I make it clear how recurrent neural networks differ from those standard models. If you can't follow the details of the 2 standard models, don't worry too much. That's not the main point. So one standard model is a linear dynamical system. It's very widely used in engineering. This is a generative model that has real valued hidden state. The hidden state has linear dynamics, shown by those red arrows on the right. And the dynamics has Gaussian noise, so that the hidden state evolves probabilistically. There may also be driving inputs, shown at the bottom there, which directly influence the hidden state. So the inputs influence the hidden state directly. The hidden state determines the output. To predict the next output of a system like this, we need to be able to infer its hidden state. And these kinds of systems are used, for example, for tracking missiles. In fact, one of the earliest uses of Gaussian distributions was for trying to track planets from noisy observations. Gauss actually figured out that if you assumed Gaussian noise, you could do a good job of that. One nice property that a Gaussian has is that if you linearly transform a Gaussian, you get another Gaussian. Because all the noise in a linear dynamical system is Gaussian, it turns out that the distribution over the hidden state, given the observations so far, that is, given the output so far, is also a Gaussian. It's a full covariance Gaussian, and it's quite complicated to compute what it is, but it can be computed efficiently, and there's a technique called Kalman filtering that's an efficient recursive way of updating your representation of the hidden state given a new observation. So, to summarize, given observations of the output of the system, we can't be sure what hidden state it was in, but we can estimate a Gaussian distribution over the possible hidden states it might have been in. Always assuming, of course, that our model is a correct model of the reality we're observing. A different kind of hidden state model that uses discrete distributions rather than Gaussian distributions is a hidden Markov model. And because it's based on discrete mathematics, computer scientists love these ones. In a hidden Markov model, the hidden state consists of a 1 of n choice. So there are a number of things called states, and the system is always in exactly one of those states. The transitions between states are probabilistic. They're controlled by a transition matrix, which is simply a bunch of probabilities that say, if you're in state 1 at time 1, what's the probability of you going to state 3 at time 2? The output model is also stochastic. So the state that the system is in doesn't completely determine what output it produces. There's some variation in the output that each state can produce. Because of that, we can't be sure which state produced a given output. In a sense, the states are hidden behind this probabilistic veil, and that's why they're called hidden. Historically, the reason hidden units in a neural network are called hidden is because I liked this term. It sounded mysterious, so I stole it for neural networks. It is easy to represent a probability distribution across n states with n numbers. So the nice thing about a hidden Markov model is we can represent the probability distribution across its discrete states. So even though we don't know what state it's in for sure, we can easily represent the probability distribution. And to predict the next output from a hidden Markov model, we need to infer what hidden state it's probably in. and so we need to get our hands on that probability distribution. It turns out there's an easy method based on dynamic programming that allows us to take the observations we've made and from those compute the probability distribution across the hidden states. Once we have that distribution, there's a nice elegant learning algorithm for hidden Markov models, and that's what made them so appropriate for speech. And in the 1970s, they took over speech recognition. There's a fundamental limitation of HMMs. It's easiest to understand this limitation if we consider what happens when a hidden Markov model generates data. At each time step when it's generating, it selects one of its hidden states. So if it's got n hidden states, the total information stored in the hidden state is at most log n bits. So that's all it knows about what it's done so far. So now let's consider how much information a hidden Markov model can convey to the second half of an utterance it produces from the first half. So imagine it's already produced the first half of an utterance, and now it's going to have to produce the second half. And remember, its memory of what it said for the first half is in which of the n states it's in. So its memory only has log n bits of information in it. To produce a second half that's compatible with the first half, it must make the syntax fit. So, for example, the number and tense must agree. It also needs to make the semantics fit. It can't have the second half of the sentence be about something totally different from the first half. Also, the intonation needs to fit. So it would look very silly if the intonation contour completely changed halfway through a sentence. There's a lot of other things that also have to fit. The accent of the speaker, the rate they're speaking at, how loudly they're speaking, and the vocal tract characteristics of the speaker. All of those things must fit between the second half of the sentence and the first half. And so if you wanted a hidden Markov model to actually generate a sentence, the hidden state has to be able to convey all that information from the first half to the second half. Now the problem is that all of those aspects could easily come to 100 bits of information. So the first half of the sentence needs to convey 100 bits of information to the second half, and that means the hidden Markov model needs 2 to the 100 states, and that's just too many. So that brings us to recurrent neural networks. They have a much more efficient way of remembering information. They're very powerful because they combine two properties. They have distributed hidden state. That means several different units can be active at once, so they can remember several different things at once. They don't just have one active unit. They're also non-linear. You see, a linear dynamical system has a whole hidden state vector, so it's got more than one value at a time, but those values are constrained to act in a linear way so as to make inference easy, and in a recurrent neural network we allow the dynamics to be much more complicated. With enough neurons and enough time, a recurrent neural network can compute anything that can be computed by your computer. It's a very powerful device. So linear dynamical systems and hidden Markov models are both stochastic models. That is, the dynamics and the production of observations from the underlying state both involve intrinsic noise. And the question is, do models need to be like that? Well, one thing to notice is that the posterior probability distribution over hidden states in either a linear dynamical system or a hidden Markov model is a deterministic function of the data you've seen so far. That is, the inference algorithm for these systems ends up with a probability distribution, and that probability distribution is just a bunch of numbers, and those numbers are a deterministic function of the data so far. In a recurrent neural network, you get a bunch of numbers that are a deterministic function of the data so far, and it might be a good idea to think of those numbers that constitute the hidden state of a recurrent neural network. They're very like the probability distribution for these simpler stochastic models. So what kinds of behaviour can recurrent neural networks exhibit? Well, they can oscillate. That's obviously good for things like motor control, where when you're walking, for example, you want a nice regular oscillation, which is your stride. They can settle to point attractors. That might be good for retrieving memories. And later on in the course, we'll look at Hopfield nets, where they use the settling to point attractors to store memories. So the idea is you have a sort of rough idea of what you're trying to retrieve. You then let the system settle down to a stable point, and those stable points correspond to the things you know about, and so by settling to that stable point you retrieve a memory. They can also behave chaotically if you set the weights in the appropriate regime. Often, chaotic behaviour is bad for information processing, because in information processing you want to be able to behave reliably, you want to achieve something. There are some circumstances where it's a good idea. If you're up against a much smarter adversary, you probably can't outwit them, so it might be a good idea just to behave randomly, and one way to get the appearance of randomness is to behave chaotically. One nice thing about RNNs, which a long time ago I thought was going to make them very powerful, is that an RNN could learn to implement lots of little programs using different subsets of its hidden state. And each of these little programs could capture a nugget of knowledge. And all of these things could run in parallel and interact with each other in complicated ways. Unfortunately, the computational power of recurrent neural networks makes them very hard to train. For many years, we couldn't exploit the computational power of recurrent neural networks. There were some heroic efforts. For example, Tony Robinson managed to make quite a good speech recognizer using recurrent nets. He had to do a lot of work implementing them on a parallel computer built out of transputers, and it was only recently that people managed to produce recurrent neural networks that outperformed Tony Robinson's ones. In this video, I'm going to talk about the backpropagation through time algorithm. That's the standard way to train a recurrent neural network. The algorithm is really quite simple once you've seen the equivalence between a recurrent neural network and a feed-forward neural network that has one layer for each time step. I'll also talk about ways of providing input and desired outputs to recurrent neural networks. So the diagram shows a simple recurrent net with 3 interconnected neurons. We're going to assume there's a time delay of 1 in using each of those connections, and that the network runs in discrete time. So there's a clock that has integer ticks. The key to understanding how to train a recurrent network is to see that a recurrent network is really just the same as a feed-forward network, where you've expanded the recurrent network in time. So the recurrent network starts off in some initial state, shown at the bottom there, time 0, and then it uses the weights on its connections to get a new state, shown at time 1. It then uses the same weights again to get another new state, and it uses the same weights again to get another new state, and so on. So it's really just a layered feed-forward network where the weights are constrained to be the same at every layer. Now, backprop is good at learning when there are weight constraints. We saw this for convolutional nets, and just to remind you, we can actually incorporate any linear constraint quite easily in backprop. So we compute the gradients as usual, as if the weights were not constrained, and then we modify the gradients so that we maintain the constraints. So if we want W1 to equal W2, we start off with them equal, and then we need to make sure that the change in W1 is equal to the change in W2, and we do that by simply taking the derivative of the error with respect to W1, the derivative with respect to W2, and adding or averaging them, and then applying the same quantity for updating both W1 and W2. So if the weights started off satisfying the constraints, they'll continue to satisfy the constraints. The backpropagation through time algorithm is just the name for what happens when you think of a recurrent net as a layered feed-forward net with shared weights and you train it with backpropagation. So we can think of that algorithm in the time domain. The forward pass builds up a stack of activities at each time slice, and the backward pass peels activities off that stack and computes error derivatives each time step backwards. That's why it's called backpropagation through time. After the backward pass, we can add together the derivatives at all the different time steps for each particular weight, and then change all the copies of that weight by the same amount, which is proportional to the sum or average of all those derivatives. There's an irritating extra issue. If we don't specify the initial state of all the units, for example if some of them are hidden or output units, then we have to start them off in some particular state. We could just fix those initial states to have some default value like 0.5, but that might make the system work not quite as well as it would otherwise work if it had some more sensible initial value. So we can actually learn the initial states. We treat them like parameters rather than activities, and we learn them the same way as we learn the weights. We start off with an initial random guess for the initial states, that is the initial states of all the units that aren't input units, and then at the end of each training sequence we backpropagate through time all the way back to the initial states, and that gives us the gradient of the error function with respect to the initial state. We then just adjust the initial states by following that gradient. We go downhill in the gradient, and that gives us new initial states that are slightly different. There's many ways in which we can provide the input to a recurrent neural net. We could, for example, specify the initial state of all the units. That's the most natural thing to do when we think of a recurrent net like a feed-forward net with constrained weights. We could specify the initial state of just a subset of the units, or we could specify the states at every time step of a subset of the units. And that's probably the most natural way to input sequential data. Similarly, there's many ways we can specify the targets for a recurrent network. When we think of it as a feed-forward network with constrained weights, the natural thing to do is to specify the desired final states for all of the units. If we're trying to train it to settle to some attractor, we might want to specify the desired states not just for the final time step, but for several time steps. That will cause it to actually settle down there rather than passing through some state and going off somewhere else. So by specifying several states at the end, we can force it to learn attractors, and it's quite easy as we backpropagate to add in derivatives that we get from each time step. So the backpropagation starts at the top with the derivatives for the final time step, and then as we go back through the layer before the top, we add in the derivatives for that layer, and so on. So it's really very little extra effort to have derivatives at many different layers. Or we could specify the desired activity of a subset of units which we might think of as output units. And that's a very natural way to train a recurrent neural network that is meant to be providing a continuous output. In this video, I'm going to describe how a recurrent neural network solves a toy problem. It's a problem that's chosen to demonstrate what it is you can do with recurrent neural networks that you cannot do conveniently with feed-forward neural networks. The problem is adding up two binary numbers. After the recurrent neural network has learned to solve the problem, it's interesting to look at its hidden states and see how they relate to the hidden states in a finite state automaton that's solving the same problem. So consider the problem of adding up two binary numbers. We could train a feed-forward neural network to do that, and the diagram on the right shows a network that gets some inputs and produces some outputs. But there's problems with using a feed-forward neural network. We have to decide in advance what the maximum number of digits is for both of the input numbers and for the output number. And more importantly, the processing that we apply to different bits of the input numbers doesn't generalize. That is, when we learn how to add up the last two digits and deal with the carries, that knowledge is in some weights, and as we go to a different part of a long binary number, the knowledge will have to be in different weights. So we won't get automatic generalization. As a result, although you can train a feed-forward neural network, and it will eventually learn to do binary addition on fixed length numbers, it's not an elegant way to solve the problem. This is a picture of the algorithm for binary addition. The states shown here are like the states in a hidden Markov model, except that they're not really hidden. The system is in one state at a time. When it enters a state, it performs an action, so it either prints a 1 or prints a 0, and when it's in a state, it gets some input, which is the two numbers in the next column, and that input causes it to go into a new state. So if you look on the top right, it's in the carry state and it's just printed a 1. If it sees a 1, 1, it goes back into the same state and prints another 1. If, however, it sees a 1, 0 or a 0, 1, it goes into the carry state but prints a 0. If it sees a 0, 0, it goes into the no carry state and prints a 1, and so on. So a recurrent neural net for binary addition needs to have 2 input units and 1 output unit. It's given 2 input digits at each time step, and it also has to produce an output at each time step. And the output is the output for the column that it took in 2 time steps ago. The reason we need a delay of 2 time steps is that it takes 1 time step to update the hidden units based on the inputs, and another time step to produce the output from the hidden state. So the net looks like this. I only gave it 3 hidden units. That's sufficient to do the job. It would learn faster with more hidden units, but it can do it with 3. The 3 hidden units are fully interconnected, and they have connections in both directions that don't necessarily have the same weight. In fact, in general, they don't have the same weight. The connections between hidden units allow the pattern at one time step to influence the hidden activity pattern at the next time step. The input units have feed-forward connections to the hidden units, and that's how it sees the 2 digits in a column. And similarly, the hidden units have feed-forward connections to the output unit, and that's how it produces its output. It's interesting to look at what the recurrent neural network learns. It learns 4 distinct patterns of activity in its 3 hidden units, and these patterns correspond to the nodes in the finite state automaton for binary addition. We mustn't confuse the units in a neural network with the nodes in a finite state automaton. The nodes in the finite state automaton correspond to the activity vectors of the recurrent neural network. The automaton is restricted to be in exactly one state at each time, and similarly the hidden units are restricted to have exactly one activity vector at each time in the recurrent neural network. So a recurrent neural network can emulate a finite state automaton, but it's exponentially more powerful in its representation. With n hidden neurons, it has 2 to the n possible binary activity vectors. Of course, it only has n squared weights, so it can't necessarily make full use of all that representational power. But if the bottleneck is in the representation, a recurrent neural network can do much better than a finite state automaton. This is important when the input stream has 2 separate things going on at once. A finite state automaton needs to square its number of states in order to deal with the fact that there's 2 things going on at once. A recurrent neural network only needs to double its number of hidden units. By doubling the number of units, it does, of course, square the number of binary vector states that it has. In this video, I'm going to talk about the exploding and vanishing gradients problem, which is what makes it difficult to train recurrent neural networks. For many years, researchers in neural networks thought they would never be able to train these networks to model dependencies over long time periods. But at the end of this video, I'm going to describe 4 different ways in which that can now be done. To understand why it's so difficult to train recurrent neural networks, we have to understand a very important difference between the forward and backward passes in a recurrent neural net. In the forward pass, we use squashing functions like the logistic to prevent the activity vectors from exploding. So if you look at the picture on the right, each neuron is using a logistic unit shown by that blue curve, and it can't output any value greater than 1 or less than 0. So that stops explosions. The backward pass, however, is completely linear. Most people find this very surprising. If you double the error derivatives at the final layer of this net, all the error derivatives will double when you backpropagate. So if you look at the red dots that I put on the blue curves, we'll suppose those are the activity levels of the neurons on the forward pass. And so when you backpropagate, you're using the gradients of the blue curves at those red dots. So the red lines are meant to show the tangents to the blue curves at the red dots. And once you've finished the forward pass, the slope of that tangent is fixed. You now backpropagate, and the backpropagation is like going forwards through a linear system in which the slope of the nonlinearity has been fixed. Of course, each time you backpropagate, the slopes will be different because they were determined by the forward pass. But during the backpropagation, it's a linear system, and so it suffers from a problem of linear systems, which is when you iterate, they tend to either explode or die. So when we backpropagate through many layers, if the weights are small, the gradients will shrink and become exponentially small. And that means that when you backpropagate through time, gradients that are many steps earlier than the targets arrive will be tiny. Similarly, if the weights are big, the gradients will explode. And that means when you backpropagate through time, the gradients will get huge and wipe out all your knowledge. In a feed-forward neural net, unless it's very deep, these problems aren't nearly as bad because we typically only have a few hidden layers. But as soon as we have a recurrent neural network trained on a long sequence, for example 100 time steps, then if the gradients are growing as we backpropagate, we'll get whatever that growth rate is to the power of 100, and if they're dying, we'll get whatever that decay is to the power of 100. And so they'll either explode or vanish. We might be able to initialize the weights very carefully to avoid this, and more recent work shows that indeed careful initialization of the weights does make things work much better. But even with good initial weights, it's hard to detect the dependency of the current output on an input from many time steps ago. So it's hard to make the output depend on things that happened a long time ago. RNNs have difficulty dealing with long-range dependencies. Here's an example of exploding and dying gradients for a system that's trying to learn attractors. So suppose we try and train a recurrent neural network so that whatever state we started in, it ends up in one of these 2 attractor states. So we're going to learn a blue basin of attraction and a pink basin of attraction, and if we start anywhere within the blue basin of attraction, we will end up at the same point. What that means is that small differences in our initial state make no difference to where we end up. So the derivative of the final state with respect to changes in the initial state is 0. That's vanishing gradients. When we backpropagate through the dynamics of this system, we'll discover there's no gradients for where you start. And the same with the pink basin of attraction. If, however, we start very close to the boundary between the 2 attractors, Then a tiny difference in where we start, that's the other side of the watershed, makes a huge difference to where we end up. That's the exploding gradients problem. And so whenever you're trying to use a recurrent neural network to learn attractors like this, you're bound to get vanishing or exploding gradients. It turns out there's at least 4 effective ways to learn a recurrent neural network. The first is a method called long short-term memory, and I'll talk about that more in this lecture. The idea is we actually change the architecture of the neural network to make it good at remembering things. The second method is to use a much better optimizer that can deal with very small gradients. I'll talk about that in the next lecture. The real problem in optimization is to detect small gradients that have an even smaller curvature. Hessian-free optimization tailored to neural nets is good at doing that. The third method really kind of evades the problem. What we do is we carefully initialize the input to hidden weights, and we very carefully initialize the hidden to hidden weights, and also feedback weights from the outputs to the hidden units. And the idea of this careful initialization is to make sure that the hidden state has a huge reservoir of weakly coupled oscillators. So if you hit it with an input sequence, it'll reverberate for a long time, and those reverberations are remembering what happened in the input sequence. You then try and couple those reverberations to the output you want. And so the only thing that learns in an echo state network is the connections between the hidden units and the outputs. And if the output units are linear, that's very easy to train. So this hasn't really learned the recurrent bit. It's used a fixed random recurrent bit, but a carefully chosen one, and then just learned the hidden to output connections. And the final method is to use momentum, but to use momentum with the kind of initialization that was being used for echo state networks. And that makes them work even better. So it was very clever to find out how to initialize these recurrent networks so they'd have interesting dynamics, but they work even better if you now modify that dynamic slightly in the direction that will help with the task at hand. In this video, I'm going to describe an approach to training recurrent neural networks that's called long short-term memory. You can consider the dynamic state of a neural network to be a short-term memory, and the idea is we want to make that short-term memory last for a long time. This is done by creating special modules that are designed to allow information to be gated in and then information to be gated out when needed. And in the intermediate period, the gate is closed so that stuff that arrives in the intermediate period doesn't interfere with the remembered state. Long short-term memory has been very successful for tasks like recognizing handwriting, where it's won a number of competitions. In 1997, Hochreiter and Schmidhuber published a paper in Neural Computation that solved the problem of getting a recurrent neural network to remember things for a long time. Their recurrent nets could remember things for hundreds of time steps. They did this by designing a memory cell that used logistic and linear units with multiplicative interactions. So information gets into the memory cell whenever a logistic write gate is turned on. The rest of the recurrent network determines the state of that write gate, and when the rest of the recurrent network wants information to be stored, it turns the write gate on, and whatever the current input from the rest of the net to the memory cell is, gets stored in the memory cell. The information stays in the memory cell so long as its keep gate is on. So again, the rest of the system is determining the state of a logistic keep gate, and if it keeps it on, then the information will stay there. And finally, the information gets read from the memory cell so that it then goes off to the rest of the recurrent neural network and influences future states. And it's read by turning on a read gate, which again is a logistic unit controlled by the rest of the neural network. The memory cell actually stores an analog value, So we can think of it as a linear neuron that has an analog value and keeps writing that value to itself at each time step via a weight of 1, so the information just stays there. The weight of 1 is determined by a keep gate, so the rest of the system determines the state of that logistic keep gate, and if it puts it into a state of 1 or close to 1, the information just cycles around, and that value of 1.73 will stay there. As soon as the rest of the system wants to get rid of that value, all it has to do is set the keep gate to have a value of 0, and the information will disappear. To store the information in the memory cell, the rest of the system has to turn on the write gate, and then whatever input is being provided to the memory cell from the rest of the system will get written into the memory cell. Similarly, to read the information from the memory cell, the rest of the system turns on the logistic read gate, and then the value in the memory cell comes out and affects the rest of the recurrent neural network. The point of using logistic units is that we can backpropagate through them because they have nice derivatives. And that means we can learn to use this kind of circuit over many time steps. So I'm going to show you now a picture of what backpropagation through a memory cell looks like. First we're going to do a forward pass. So at the initial time, let's suppose that the keep gate was set to 0, so we wiped out whatever information was in the memory cell before, and the write gate is set to 1, so the value of 1.7 that is coming from the rest of the recurrent neural network gets written into the memory cell. And we're not going to read it at this time, so the read gate is set to 0. We then set the keep gate to 1, or rather the rest of the neural network has to set the keep gate to 1, and that means that the value is written back into the memory cell. It's stored. At the next time step, we're going to set the write gate to 0 and the read gate to 0, so the information isn't influenced by what's going on in the rest of the net, and it doesn't influence what's going on in the rest of the net. It's insulated. Again, at the next time step, the keep gate is set to 1, so the information is stored for one more time step. And then we're going to set the write gate to 0, so no information is written in, but we're now going to retrieve the information by setting the read gate to 1. The value of 1.7 then comes out of the memory cell and goes off to influence the rest of the network. And if we don't need it anymore, then the keep gate can be set to 0 and the information will be removed. Now, if you look at the 1.7 that comes out when we do the retrieve, and you look at the path back to the 1.7 that came in, along that path there's these little triangular symbols, and next to each triangular symbol there's a 1. That means that the effective weight on that connection is a 1. So as we go back along that path, whatever error derivative we have for the 1.7 when it's retrieved gets backpropagated to the 1.7 when it's stored. So if you'd rather have retrieved a bigger value to make the right things happen now, you can send the information back and tell it should have stored a bigger value. And notice that as long as the relevant gates have values of 1, there's no attenuation in this backpropagated signal. It's got just the properties we want. Of course, if they're logistic gates, there will be some slight attenuation, but it can be very small, and so information can travel back through hundreds of time steps. Now let's look at a task that a recurrent neural network with long short-term memory is very good at. It's a very natural task for a recurrent neural network. It's reading cursive handwriting. The input is just a sequence of the x and y coordinates of the tip of the pen, plus some information about whether the pen is on the paper or not. The output is going to be a sequence of recognized characters. Graves and Schmidhuber in 2009 showed that recurrent neural networks with long short-term memory are extremely good at this task. So far as I know, they're currently the best systems there are, and I believe Canada Post is starting to use them for reading handwriting. Graves and Schmidhuber in 2009 didn't use pen coordinates as input. They used a sequence of small images, and that means they can deal with optical input where the timing of the pen isn't known. They can look at images after they've been written and read them. So I'm now going to show you a demonstration of Alex Graves' system working on pen coordinates, and in the movie that follows you're going to see 4 streams of information. The top row shows the characters as they're recognised. The system never revises its output, so if it has to make a difficult decision, it delays it for a little bit so that it can see a little distance into the future to help it resolve ambiguities. The second row shows the states of a subset of the memory cells, and you should notice how they get reset when it recognises a character. The third row shows the actual writing, and all the net sees is the x and y coordinates of the tip of the pen, just 2 numbers, plus some information about whether the pen is up or down. Finally, the fourth row shows something much more complicated. It shows the gradient backpropagated all the way to the x, y locations. So what you get to see is, for the most active character, if you backpropagate from that character and ask what would make that most active character more active, you get to see which bits of the input are affecting the probability that it's that character. So that lets you see how the decisions are depending on things that happened in the past. So here's the movie.